So, did you ever wonder what would happen to the world of computing without the powerful data centers? I'm sure we won't sustain with the amount of data being generated these days. So, let's address this issue today and see what the paper has to offer. I'm Deepen Panchal, and with me is Shreyash, and we are going to have a discussion about the solution provided in this paper. The title of this paper is Memcached GPU Scaling Up, Scale Out Key Value Stores, and the authors are right in front of you right now. So, let's jump in. So, what is this about? But before we jump in, let's first establish the difference between GPU and CPU. GPU, the full form is graphic processing unit, which has higher tendency to work with key values, which enhances its processing power and gives better performance than a CPU, which is exactly why it is used in games these days. Now we'll be talking about that in detail in a while. But let's see how is Memcached GPU, which is the title of this paper, helping in this case. So Memcached GPU is more efficient in data centers because it maintains low latency and provides high throughput while conserving significant amount of energy. Okay, so talking about data centers. So what are they and why do they consume so much energy? Data center is a dedicated space where we house a lot of servers to support the real world applications which we constantly use every day, and they consume so much energy obviously because of the huge amount of data being generated, which is just ever growing. So it takes larger processors to process the data, and hence the energy consumption is increased, and it is very essential to reduce the energy consumption considering the amount of data that is growing every day. So it will require more processors, and which is why we need more energy efficient data centers. Now let's just establish the terms that we'll be using throughout in this presentation. So what is ASIC and what is an FPGA? So ASIC is application specific integrated circuit and FPGA is field programmable gateway array. And these both are similar to GPUs, but obviously not as efficient as GPU. Now FPGAs are much better than ASICs because they can be programmable for different applications, whereas ASICs are specific for applications because the name suggests, application specific integrated circuit. So are GPUs compatible to high level languages? Yes, we use high level languages like CUDA and OpenCL. I'm not sure if it's that's how you pronounce it, but yeah, CUDA and OpenCL to program applications over FPGAs as well as GPUs. So how does the GPU process the requests? So GPU uses request level parallelism through batching to process multiple concurrent requests, and also we can achieve task level parallelism within a single request to improve latency. Now let's move on to Memcached GPU. Memcached is a general purpose scale out in memory caching system used in distributed database system to improve performance by reducing the amount of traffic to backend databases. Now, before we move on to NIC architecture, let's just talk about how data is stored in Memcached GPU and how it is accessed. So we get a key value store interface in Memcached GPU to modify and retrieve data from the hash table. Now Memcached uses a custom memory allocator from pre-allocated memory slabs to store the items. To avoid memory fragmentation, Memcached allocates multiple memory slabs with different fixed sizes entries. Another term that we'll obviously see in this paper is NIC. So the what is NIC? NIC connects to the host CPU via PCIe bus. Packets enter receive queues at NIC, and NIC sends interrupt to the CPU for one or more pending receive packets. There's an NIC driver which copies packets to Linux sockets and returns the uh, receive packets back to the NIC. Now let coming to the GPU. Now this is a very essential part of this paper because we're talking about Memcached GPU. So what is a GPU and what can GPUs do? You know, GPUs are designed for graphics, as the name suggests, graphic processing unit. But recent GPUs can also run non-graphic applications like CUDA and OpenCL, the high-level languages we were talking a while back. In this paper, the author has used CUDA and NVIDIA GPUs, but the system can also be extended to AMD GPUs. It's not only uh, you know working with NVIDIA GPUs. Now, uh, CUDA applications are composed of two parts: the host side and the device side. The host side is responsible to initialize the GPU environment and communicate with the GPU, and the device side is the one which executes one or more kernels. There's something else which we also talk about in this paper, which is genome. What is it? It's GPU Network Offload Manager. Genome incorporates UDP network processing on GPU. It also provides a software layer for efficient management of GPU tasks and network traffic communication directly between the NIC and the GPU. The use of genome enables a high throughput, low latency, and energy efficient UDP processing. Now, there's something called as request batching in genome. Request batching in genome handles smaller batch sized to reduce the latency. Smaller batch sizes to reduce the latency. Let's see the software architecture of genome. Now, genome in the diagram, as you see, consists of two main parts: the genome host and the genome device. We'll be touching on to genome host and genome device in detail in the following slides. Uh, but let's just see what each of those do. The genome host, which is responsible for it is responsible for the interaction with NIC and the GPU data and task management. The second part is genome device, which is responsible for UDP packet and application processing. Now, this diagram shows the interaction between NIC, CPU, and GPU in genome, as well as the main CUDA kernel. Let's move on to seeing in detail what the genome host does. So the host provides task management and I/O support to the GPU because GPU can't directly communicate with the NICs. So to do this, genome comprises of a network driver, a custom Linux, a kernel module, and a user level software framework. What is a genome device? A genome device leverages additional helper threads to perform parallel tasks related to single network service request, exploring both packet level and task level parallelism. Now, this improves the latency. It helps warps into main and helper warps. So the main warps perform the network service processing, whereas the helper warps perform UDP processing and response packet header construction. So that is where the UDP response header is constructed. Now, in this diagram, let's see how exactly the Memcached GPU works. The GPU memory over here, so it's divided into GPU memory and CPU memory. The GPU memory, which you see over here, is used for GET requests. Now, what is GET request? GET request is the retrieval of data which is already in the memory. Now, CPU memory over here is used for set requests, which is basically set requests are basically to modify the data, which is adding the data and deleting the data or modifying the data. Now, so why are the get requests on GPU and set requests on GPU? Why are both not done in the GPU, and vice versa? So because in typical Memcache deployments, get requests comprise a large fraction of traffic when hit rates are high. So more focus is on accelerating the get request because it's larger in number, and because GPU can handle processing better than CPUs. So it is done in GPUs, and set requests are handled on GPUs. So like I mentioned, GPU get requests are handled in the GPUs. These what are these requests? They include passing the get request, extracting the key, hashing the key, and accessing the hash table to retrieve the item pointer. Now, because set requests are on the CPU, they require special attention to ensure consistency between CPU and GPU data structures. Obviously, because of the difference in the frequencies. Uh, Set requests update the GPU hash table by launching a naive set request handler on the GPU, but it first allocates the memory slab in CPU memory and then updates the GPU hash table. It doesn't directly update the GPU hash table. Now, talking about hash table. So uh, Memcached GPU also employs the hash table, uh, as similar to the baseline, the typical Memcached deployments. But what is the difference? So so the modifications to the baseline Memcached hash table is to make the processing on the GPUs efficient. So what is the main difference between that one and this one? So the main the baseline Memcached implements a dynamically sized hash table with hash chaining on collisions. It resolves collisions by dynamically allocating new entries and linking them into existing linked list, at conflicting hash table entries. But this is a poor fit. Now, why exactly is this a poor fit for the GPUs? Because dynamic memory allocations on current GPU can significantly degrade, performance if you dynamically allocate memory on the GPU. Also, hash chaining creates a non-deterministic number of elements to be searched between requests when collisions are high. So how are these addressed in Memcached GPU? So Memcached GPU, it implements a fixed size set associative hash table. Now each hash table entry contains a header and a physical key. The header contains a valid flag, a last access timestamp, the length of the key value, and a pointer to the item in the CPU memory. Now, talking about get requests and set requests in this case, get requests do not modify the hash table entries, and so multiple get requests can access same hash table entry concurrently as they have similar timestamps. So, which is why this implementation of the hash table is better. But set requests require exclusive access since they modify the entries. So to handle this, what Memcached GPU does is that there's a multiple shared trader single writer spin lock for each hash set is employed using CUDA atomic compare and exchange increment and decrement instructions. So now uh, we talked all about Memcached GPU and how it handles the get and set requests and what is the data structure, which is the hash table that we were talking about, and how it is actually better than the traditional style of the hash tables in typical Memcached deployments. So let's see how this author has done it. I mean, so let's see how it stands with the competing ones. That Let's see the evaluation with Shreyash now.
Hi, my name is Shreyas and I'll be taking over it from here. First, we'll be talking about the evaluations that are to be done, as mentioned. So, first, we look at the methodologies that have been used to calculate and implement these. So, as we can see, the server and client configurations are presented, and we use two GPUs. One is Tesla, and the other is GTX 750 Ti, which are evaluated using a genome for the Tesla and NJD for the GTX. We also find that ASCII protocol is used with a minimum key size of 16 bytes. However, we find that genome becomes network bound, not CPU bound, as value size increases. As we can look at, we created a custom client Memcached stress mark using pfring 0 copy for sending and receiving request packets at 10 Gbps and replay traces of set and get requests generated from Memaslab. However, processing all response packets still limits our send rate to 6 Gbps. For calculating the power, we measured the ideal power of the Tesla K20 and GTX 750 using the wall power meter and the NVIDIA SMI tool and subtracted the inactive GPU idle power from the total system power when running experiments on the other GPUs. Now looking at hash tables. We evaluate the hash table using two methods. One is hash chaining and another is set associative. Looking at HC, we see that evictions only occur when the total number of elements is exceeded. However, evictions may occur for the SA hash table even with fewer elements than the maximum due to set conflicts. We generated a runtime trace of 10 million key value pairs with 95% get requests and 5% set requests. We see that with a maximum hash table size of 8 million entries, SA has 21.2 miss rate with one way and 10.4% miss rate with 16 ways. HC achieves a 0% miss rate when the hash table size is larger than the request, since it is able to allocate a new entry for all new key value pairs. As the hash table size increases, increasing the associativity decreases the miss rate. At 16 ways for all sizes, SA achieves a minimum of 95.4% of the HC hit rate for the zip distribution. Now we'll be looking at the Memcached GPU evaluation. In this, we'll be looking at the latency, the throughput, the energy efficiency, and branch divergence. First, we look at the latency. While the GPU is a throughput oriented accelerator, we find that it can provide reasonably low latencies under heavy throughput. Genome has lower latencies than NGD at P95 on the Tesla by reducing the number of memory copies on packets RX with GPU Direct. As the throughput approaches the 10 GB line rate, the latency also increases, with the P95 latency 1.1 millisecond with Genome and 1.8 millisecond with NGD. At 2 MRPS with a batch size of 512 requests, the average batching delay per request is already 128 microseconds compared to 32 microseconds at 8 MRPS. While not showing here, a simple timeout mechanism can be used to be used reduce the impact of batching at low requests while launching partial full batches of requests. Now looking at the throughput. Memcached GPU is able to process packets near 10 GB line rate for any Memcached request size with server packet drop rates less than 0.006% for Genome and zero point 0.5 for NGD. The client drop rates are measured using the static trace with no packet loss at the server. Now looking at the energy efficiency. The Tesla K20C power increases by less than 35% when increasing the throughput by 13 times, leading to the steady increase in energy efficiency. The jumps in system power at 10.1 and 12.9 MRPS are caused by adding genome post threads to recycle the GRXBs fast enough to maintain low packet drop rates at the higher throughputs. At peak throughputs, the low power GTX 750 Ti uses NGD consumes 73% of the total system power consumption by the Tesla K20 using Genome. The Tesla K20C consumes roughly one third of the total system power. Now moving on to branch divergence. Differences in key length, potential hits on different indexes in the hash table, set or misses in the hash table, can all cause threads to perform a different number of iterations or execute different blocks of code at a given time. We find that the throughput performs with 99% of the theoretical peak regardless of the key distribution. That is, even when introducing branch divergence, Memcached GPU becomes network bound before compute bound. The results match the intuition that because there is no sorting of key lengths to batches, the latency should fall somewhere between the largest and the smaller key lengths in the distributions. Now looking at the get and sets. The maximum set request throughput is currently limited to 32 kilo requests per second in Memcached GPU. Improving set support is the left to the future work. Table 4 presents the get and set request throughputs resulting set get ratio and server packet drop rate of Memcached on the GPU. The low maximum set request throughput limits the set get ratio to less than 0.5% for higher get request rates. The average server packet drop rate approaches 10% when increasing get throughput to 90% of the peak, which limits the effectiveness of Memcached GPU. Get requests at 9 MRPS maintain comparable drop rates to the peak throughput while also handling 0.26 set requests. Now we'll be looking at workload consolidations on GPUs. Workload consolidation is running multiple workloads concurrently on the same hardware, improving data centers' utilizations and efficiency. Long reconfiguration times for of reprogrammable hardware, milliseconds to seconds, may mitigate the benefits gained by the accelerator when switching between applications. In this, we use multiple CUDA applications to be implemented. Large CUDA kernels with many CTAs may consume all the GPU resources, blocking another CUDA kernel from running and complete. If we reduce the background task to 16 CTS per kernel, we require 16 separate kernel launches to complete the task. The average client RTT based on a 256 request window during the background task execution. Without the background task execution, Memcached GPU has an average RTT of less than 300 microseconds with the 256 CTS. The BGT consumes the GPU resources, causing a large disruption in the RTT. Even after the BGT completes with 256 CTS, Memcached GPU takes over 20 milliseconds to return back to the original average RTT. The BGT execution time with and without Memcached GPU, as well as the maximum average RTT seen by Memcached GPU during the BGT execution at 4 MRPS, Memcached GPU has very little impact on the BGT execution time due to its low resource utilization and small launches. Now moving on to the offline limited study. The same pack trace used in previous section with the minimum key size of 16 bytes to stress genome is used in the offline evaluation. Each GPU achieves over 27 MRPS, suggesting that the GPUs are capable of handling over 2 times the request throughput measured in the online evaluation. An interesting result of this study was that the low power GTX 750 reduced the average batch latency compared to the Tesla K20 by 25%, while also slightly improving peak throughput. The GTX is able to process over 27% and 43% more GET requests per watt than the Tesla K20 and GTX Titan. Now looking at the previous work and comparing to it. So we can see these results highlight that while bypassing the Linux network, stack can increase performance and energy efficiency. Additional optimization to the core Memcached implementation are required to continue improving efficiency and scalability. The CPU and FPGA process request serial requiring low latency per request to achieve high throughput. The GPU instead processes many requests in parallel to increase throughput, as such applications with very low latency requirements may not be a good fit for the GPU. Memcached is able to closely match the throughput of an optimized FPGA implementation at all key and value size while achieving 79% of the energy efficiency on the GTX 750i. Additionally, modifications such as the log based value storage could also be implemented in Memcached GPUs. In contrast, all of the UDP packet, data movements, and processing is still included in the offline Memcached GPU study. However, UDP packets are read from CPU memory instead of over the network. In the offline analysis, the GTX 750i may improve cost efficiency over Mika up to 27%. Now, looking at some of the related works that have been done, we look at some important details that have been done. The GPU is only used to perform a parallel lookup for the corresponding CPU key value pointer in a GPU cuckoo hash table. All other processing, including UDP network processing, request passing, key hashing, and key comparisons, are done on the CPU. In contrast, the goal of our work was to achieve 10 GB line rate performance of all key value sizes while performing all of the UDP network processing and GET request processing on the GPU. So most of the part of set requests were done on the CPU as explained by Deepen, and the GET requests were implemented on the GPU. Now looking at another bigger prospect, GPU net, a networking layer and socket level API for GPU program. GPU net aims to improve the support for applications requiring network IO on GPU accelerators. Now looking at Packet Shadow. He implements a software router framework on GPUs to accelerate lower network layer, whereas Genome and Memcached GPU focus on transport and application levels. In contrast, this work performs all Memcached gets requests and network processing on the GPU, addressing many of the challenges associated with a full system implementation. Prior work has evaluated server workloads on GPUs such as Memcached HTTP workloads or database queries. They focus solely on the workload specific processing. In contrast, this work considers a full system implementation, including end to end network measures. While the focus of this paper is on Memcached, one of the long term goals of our work is to provide a general framework for accelerating high throughput network services on GPUs. This is has been studied very much, and there are many citations that are presented, which is a lot. And there are many studies that have been done to for an implementation of better GPUs and better hash table key value storing systems. Now, in conclusion of the paper, this framework allows a single GPU equipped data center node to service network requests at 10 GBE line rates while maintaining acceptable latencies even while processing background lower priority batch jobs. We, we believe that future GPU enabled systems which are more tightly integrated with the network interface and less reliant on the CPU for IO will enable higher performance and lower energy per request. So this paper was basic study of implementation of more of the processing part on the GPU to enhance the speed, as the CPU has to be used for accessing and updating data sets, but the GPU can process them faster and get the request completed faster. And this can be seen as the throughputs that we have noticed in the evaluation part. Thank you and have a nice day.
So, to conclude, I would like to say that the paper is very useful as it is already being implemented by big technology giants like Facebook and Google. We already know that GPU are much more efficient than CPU as they are used to perform higher graphic processing and are already being used in machine learning. This paper exactly explains us that, and the future advancements in CPU designs are with enhancements in GPU and the use. This paper would be a good read for students and researchers who are looking to increase their performance in computing while reducing the energy costs. That's me, the pen signing off. Thank you.